Hello everyone, my name is Timothy Lee Grant. I am so happy. I just got done solving, which one was it? It was Path Sum. I finally got it. I've been on a losing streak. I had failed over, I think 5 times in a row. I failed. I couldn't get it. Couldn't get it. Nope, nope, nope. And then I finally, just now, few moments ago, few seconds ago, I solved this one right here, broke my losing streak. We are back at it, back, back, back. It is time to do another LeetCode and capitalize on this momentum. Okay, so let's see, which one should we do? I am not doing a medium because I am happy right now. I do not want to lose that energy. Okay, we are doing an easy. Easy, easy, easy. Okay, closest binary search tree value. Let's try it. Okay, it's an easy. I like that. I like it. Ah, never mind. We're not doing it. Let's see. Which one are we going to be doing? Oh, come on. Oh, here's another easy. Okay, here we go. Here we go. Here we go. Here we go. Let's not break it. We finally broke our losing streak. It's time to do our. It's time to not break our winning streak. We're gonna keep it. We're gonna keep it going. All right. Number 404. Sum of left leaves. Okay. Given the root of a binary tree, return the sum of all left leaves. A leaf is a node with no children. A left leaf is the leaf that is the left child of another node. Okay. Return the sum of all left leaves. Okay. Now, so this is our goal right here. The sum, so I'm going to be returning an integer. This integer represents a sum. This sum is comprised of the values of all left leaves. Okay, so I need to define for myself what is a left leaf. That's in the next sentence. It says, a leaf is a node with no children, right? That's standard for a tree. A leaf means no children nodes. Now, a left leaf is a leaf, so a node with no children, that is the left child of another node. Now, my question immediately is going to be, okay, so this one would be would not be a left leaf, right? Because it would be right, right, so it is not a left child of any node. What about something like this, where we have this value, the root value, we come down here, that's a left, right here, we have left, but what if we go right? What if there was a node here? Does this count as a left leaf? Because it is a left child, or grandchild, I guess. So maybe that means no. So left child, right child. Does this count as a left leaf? I think that would be no, because it's not inheriting it from its parent. It's only looking at one layer above. So that's my immediate question, and now I'm going to go and look at the examples and try to confirm or deny the question which I have and see if I am on the right track. Okay, so here's the graph. 24. So there are 2 left leaves in the binary search, or in the binary tree, with values of 9 and 15. So that is accurate because this one has its left child, is a left child, and this one is a left child. The question which I was having is regarding if this is a left child. So this graph doesn't actually have that particular scenario. But I am just going to guess that no, when it says left leaf, it only means this another node. I don't know, that phrasing right there, of another node. It doesn't say of the parent node. It just says another node. Which, at least from what I'm thinking, it sounds like it would be, based off of the sentence, the grammar sounds like it is any path. If there was any left shenanigans anywhere along the path to the root, you are considered a left leaf once you hit the leaf. So like I went left here, any path below this 9, so it's left or right, all those leaves below 9, pretend that, or let's just say like this, like let's say that this 3, there was actually a root node up here. So there was a root node here, and it was the left root node. Therefore, this is going to be a left leaf, this is going to be a left leaf, and this is going to be a left leaf. Even though it's right, left. And that left, that's what I'm curious about. That's what I'm wondering. But that's also not helpful, because that doesn't give me the answer that I'm looking for regarding that clarification question. Okay, so moving forward with solving this problem, I'm going to have to just assume what the question is asking. We're going to submit it, and then we're going to see if it works. If it does work, great. If it doesn't, then we're going to change it to be the other assumption. So that's kind of how I'm going to be moving forward with this question. All right, so enough chitter chatter with that. Let's get to coding. How do I want to actually code it? So with sum, I need to so sum value equals 0. So we're going to start at 0, and then we're going to have def recurse, and in this recurse we are going to pass in the node. Okay, so now what are we going to do? We are going to return self.sum value. And in the last problem that I just finished like a few minutes ago, literally I solved one problem, and then I said I'm going to stop the video, and then I'm going to start another video, and that's this current video. Kind of reminds me of recursion. I'm talking about this video, but referring to the video above it. Anyways, I have recursion in my brain. I've been doing this all day. I've been doing problem after problem after problem. So my brain is completely soaked with recursion right now. I feel like such a nerd. I'm talking about making YouTube videos, and I'm describing another video, and somehow that makes me think of recursion. Anyways, I lost my train of thought. What was I even talking about? Oh, right. Last video. I was solving a problem, and I was really excited. I felt good about it. I felt happy. I felt confident, and I pressed that submit button. I didn't even press the run button. I pressed submit, and then rejected. In the video, I was actually kind of like, uh-oh, because I was thinking like I was pretty confident in my answer, but I got it wrong, and I was thinking like, okay, what's going on? Why is it like this? That doesn't make it. And there was no like visualization. The problem that I failed on, or the test case that I failed on, there was no visualization, so it was just like it passed on the everything else, but I what was going on? Why is it not doing this? And so I was thinking, how am I going to even walk through this code? I was getting kind of worried. And what it was, I said, okay, well, let me just try something. I had a variable that was very similar to this, and I was changing it in a helper function here within this. So it was a function within a function, and I was in this function changing this value. Okay. And there was some problem with the scope and returning the value. So what I did was I went self dot this variable and then changed this inside this to be self dot like that, and then it passed. So lesson learned is create that self. I should also kind of just like take time to figure out like, okay, within a function within a function, kind of a weird thing. I'm trying to think back if in any of my projects I've ever actually done that. I don't think I have. Well, okay, JavaScript, but JavaScript is a completely other thing. All of those anonymous functions, all of those callback functions. Okay, I'm not talking JavaScript. I'm talking like Python development. Have I ever done a project where I use a function within a function? And I think the answer is no. The only time that I've actually done it is with these like LeetCode problems. So I'm a little bit fuzzy on the rules regarding variables within, it's within the same class, and it's within this, can I call it a parent function? It's within this sum value is within this parent function, but do I have access to it within this function which is inside the parent function? I don't know. So I'm a little bit fuzzy on the rules. I'm going to have to look that up, try to figure out why it failed. But I know that if I just do self, that I can make this variable here a member of this solution class, and therefore the scope is kind of like global to that class. So I'm able to adjust it wherever I want, and it will retain its value. So all right. I've been talking so much I almost forgot what the problem was asking. Okay, a left note. Oh, right, we're summing up the left notes. Okay, so I'm gonna go something like this. Actually, I'm gonna go like this. Is left. All right, so now what this is left is going to keep track of is if there has been any left shenanigans going on in the path leading up to the node that I am currently at. So then once I get to a node, let's take this one. This is the right. So I pass in this as my root, and initially I have this as false. So I pass false in, and then I go down here and I continue to keep passing false. The only time that I pass true is if I start here and is left is set to false. Then when I come down and do a left operation, I change that and then I say true. So that way I can determine, okay, this is a left child. In this one's case, I go right and it's still false. I go right, it's still false. I'm going to say, okay, this is a leaf node. I'm not going to keep recursing. But because this is left is set to false, I'm not going to add this to the sum. This one, we have here and it's false. We come here and it's left. It's a left operation. So all of a sudden I'm going to say, yes, this is true. So I'm going to pass true in. Okay? Now, let's consider this node, but there is a root. The root node is up here, and it's connected through a left. So I'm going to go left, and this is going to be true. So now, is left is true. Then I go right, and this is still true. So that true value is kind of sticky. So the left is a sticky variable that only changes one time when we do a left operation, and then it retains its value. So the way that I'm going to do that is kind of like this. So if, well, first I should call the function. So recurse and then root false, but I only want to do that if the tree exists. Are we guaranteed that the tree exists? So the number of nodes within the tree is 1 to 1,000. So we're guaranteed that this root exists. So I'm not going to do blocking like if root, then recurse, else return false. I'm not going to do that, or return 0. The reason is because in the constraints it's guaranteed that we have at least one node in the tree. So I'm just going to recurse on root. Then I'm going to check if not node dot left and not node dot right. So in this case we are a leaf node. We've hit a leaf node, but we need to determine if we are a left leaf node. So if is left, and this is only going to be true if we have hit, or if we've done any left shenanigans along the path down the tree. So if is left, then we are a left leaf. Okay, so what do we want to do? We want to do self.sum value plus equals and node.val. Okay, and then return. So this is a base case because it is a leaf node, so we don't want to keep recursing, so we just return. Now we need to continue down the path. So we haven't hit, we're not a leaf node, we have a left or a right child. We need to recurse down the left or the right or both. So let's do that. So if node.left, so if there is a left node, what do we want to do? We want to recurse down the left path. So recurse, and then we do node.left. So we're going down the left, and now here's that sticky value. We want to do true. We want to return, or we want to pass true. Okay. So now if node.right recurse node.right, is that going to be false? I know it is not going to be false. sticky value equals wait, I can do this. I can do is left. Okay, yes. I can do is left because I initially started off to be false. I initially started off to be false right here. And then if I go down and I hit a left, then I'm changing it to be true. So now this value is going to be true. And I am going to have this to be, this value here is now going to be continually true. All the way down. But if it's false, it's going to retain its value of falseness. This one is always going to be set to true because you've gone down a left path. Regardless of if the previous values have a left in them, now it is true. Submit? Do we submit? Let's try it. Let's try it. Oof. Okay. Okay, well, we got that wrong. Chug the coffee. Oh, man. Is it that maybe it's our assumption? Maybe our assumption was wrong. Okay, let me just try this right here. So def recurse 2, and we have node here. Now, maybe it is the case that we do want to only look at if the parent is the left. So now I can essentially just do the same thing. So in this case, I want to, this is a base case, so I need to check. So if is left like this, and then add it. Okay, but how do we determine is left? We need to have a way to actually determine that. That should... well, we just don't make it sticky. Yeah, we can just like do this same thing, just don't make it sticky. I think that'll work. So copy this entire thing. Let's see. And then I'm going to call this recurse2. And then, let's see, recurse here. So this is going to be recurse2. And now I just do, so that's going to continue to be true, but I now want this to be false. And the reason is because now I don't want to retain the value of the previous paths above it. I just want to say you are going right. You are a right child. Therefore, you're not part of this club. You're not part of the left club. Okay, so recurse. And now I'm going to do 2. And some value is still going to be manipulated. So I'm going to do that. And let's see what's up. Oh, okay. So it was the assumption. Yeah, the way it was phrased, I still think, like, listening to the grammar, it feels like it meant any child above it. But apparently not. So we got the answer. It was meaning just its immediate child. So kind of what, I guess I can go and explain a little bit more. So what I meant was, if there was a node here, and it doesn't matter that I went left here. If I go right here, this is not considered a left leaf. It sounds like a left leaf is a leaf that is the left child of another node. So it only means child, meaning the one immediately above it. So there we go. Solved it. I want to get back to that. Where does it say accept? There we go. I like this. This is how I want to end off. I want to end off on this. Oh, I'm so happy. I'm so happy I got it. There we go. I kept my winning streak. I kept it. I kept it. I kept it. We got 2. We got 2 under up belts now. I failed 5. And then I broke it finally about 20 minutes ago. How long is this video? I don't have a counter on it. But anyways, however long this video is, I broke my losing streak. That got 1. And now, bam, I got another one. I'm on 2. Now I'm on a winning streak. Got it. Okay. I am going to, so yeah, thank you guys for watching this video. My name is Timothy Lee Grant. Subscribe. That would be awesome if you would subscribe. I am going to continue the momentum. I'm going to be making another LeetCode video, continuing to do depth first search. My idea is, because I kept failing and failing and failing and failing, I am going to just focus on one subject, just do one thing, and not get distracted by any of the other problems. Not breadth first search, not oh, what are the other ones? Like the one that I was doing is the I forgot what it was called. Hold on. I was doing a lot of the, not like greedy. What was I doing? Heap. I did heaps, 2 pointers, dynamic programming, like not just doing random things, but what I think I might do is just focus on depth first search and get it to the point where I am really good at this. I can solve, if it's a depth first search, I can solve it. Get to that point. Then once I'm at that point, move on to another one. Move on to maybe breadth first search or something like that. But first, I'm going to get good at this. So I'm going to keep my momentum. I'm going to do another video coming out. So yeah, see you guys very soon. Have a wonderful day. Goodbye. So happy.